Welcome to the discovery of photoelectricity. Newton was an English physicist. He was the first person to publish about the fact that different colours absorb light differently. He noticed that the colour black absorbs energy better than other colours. Leslie did a little bit more work on this, and he even produced a piece of experimental equipment to test this theory. It consisted of a cube that was hollow and had a hole at the top into which he poured boiling water. The different sides of the cube were coloured in different ways. There was a silvered side, a shiny coloured side, and there was a matte black side. And he noticed that if he placed a thermometer in front of the matte black side of the cube, even though the whole thing was at the same temperature because it had boiling water poured into it, and that water was in contact with every side of the cube, he noticed that if you place the thermometer in front of the matte black side, it reached a higher temperature than on the silvered side. And this meant that the matte black side was a better radiator of heat than the silvered side. It emitted more energy. Kirchhoff, a German physicist who's better known for his laws of electricity, he developed the law of thermal radiation. He noticed that the absorptivity was equal to the emissivity. That means that if you have a surface, then it absorbs heat just as well as it emits heat. And he posed the question, how is the intensity of the heat, the wavelength of the waves given off, and the temperature of the object, how are these variables related to each other? Jeans was an English physicist, and he developed another piece of equipment called the Jeans cube. It was a hollow cube with a very small hole on one side, and this hole acted as a black body. A black body is a theoretical object that has the properties such that when light falls upon it, none of the light is reflected, none of the light is transmitted, but 100% of the light is absorbed into the material. Now, with this very small hole in the cube, light is able to enter through that very small hole and then will reflect inside on every surface. The chances of it being able to escape are very, very small. So this is an excellent approximation of a black body. Almost all of the energy that enters this cube is retained inside of it. And if you heat the cube so that it is hotter than its environment and energy would flow out, then any energy that is escaping through that hole is sampling all of the wavelengths that are inside the cube, meaning that the cube is acting as a black body for both absorption and emission. And this piece of equipment allowed experimental research to be done on the different wavelengths and intensities of emissions from a black body, in the hope of answering Kirchhoff's questions. Lummer and Pringsheim, both German physicists, were able to use the Jeans cube to collect experimental data. They showed that at low temperatures, you get a flat curve of intensity against wavelength, and at higher temperatures, you get steeper and higher curves. Stefan and Boltzmann, an Austrian and German physicist, produced the Stefan-Boltzman law, which is an equation where we have the energy radiated per unit area being proportional to the temperature to the power of 4, and this is known as the Stefan-Boltzman constant. Wien, another German physicist, he was able to analyse the shape of one of these curves and predict where the peak would be for all subsequent temperatures. And he did that using an equation with Wien's constant. Up until now, the shapes of the graph had been largely found through experimental means. Parts of the graph were able to be described mathematically, but only parts. And the physics community were keen to be able to mathematically describe and predict the shapes of these curves. So Jeans and Rayleigh, who's an English physicist, attempted to do this, and they used the most up-to-date physics. Their idea was that inside the Jeans cube, light has established itself as a series of standing waves. Many, many, many of them. So they used Maxwell's ideas about light being a continuous electromagnetic wave, and Boltzmann's statistical ideas about how to calculate the average energy when you have a lot of objects to calculate for. The result of their analysis yielded a very good estimate at high wavelengths. But this very soon departed from observed values and went very, very high and tended to infinity for very short wavelengths. And this, because it was occurring in the very short wavelength area where you get UV light, this overestimate of intensity was called the UV catastrophe. And it was a catastrophe because this prediction was based upon cutting-edge physics, and nobody could understand what was wrong with the mathematics. Planck was a German physicist, and he says, "I knew that the problem was of fundamental importance to physics." He struggled for 6 years, wrestling with mathematics, trying to get the predicted data to match the experimental data. And he said that in an act of desperation, he adapted the mathematics to make it work, and it did. But one of those changes that he had to make was this equation. Previously, it was thought and modelled that the energy of the standing waves inside the Jeans cube could have any value of energy. But he modelled that the energy must be a multiple of these two numbers multiplied together. And if that's the case, then energy cannot hold any value. It is not a continuous variable. Instead, it is a quantized variable. It can only hold certain values, and those are multiples of hf, h being Planck's constant. Koblenz, an American physicist, experimentally proved Planck's predictions. The dark line on this graph are Planck's calculations, and the points are the experimental measurements made by Koblenz. In 1918, Planck was awarded the Nobel Prize for Physics. Planck's idea about energy only being able to hold certain values was the start of quantum physics and the birth of modern physics. Born an early quantum physicist, said about Planck, he was by nature a conservative mind. He had nothing of the revolutionary and was thoroughly sceptical about speculations. Yet his belief in the compelling force of logical reasoning from facts was so strong that he did not flinch from announcing the most revolutionary idea which has ever shaken physics. Born himself won the Nobel Prize in 1954 for his work on quantum physics. 5 years after Planck published his ideas, Einstein used the idea to solve the problem of photoelectricity. When Einstein published this work in 1905, he wasn't working as a professional physicist, but his wife, Mileva Maric, was. He was working as a clerk in a patent office at the time. In 1921, Einstein was awarded the Nobel Prize for solving the photoelectric effect, but it's worth noting that he gave the prize money to Mileva. Previous to Einstein's paper, the photoelectric effect was not well understood, and this is because physicists had been attempting to describe it using the wave theory of light, just like the black body radiation curves. Now that Einstein was able to use a quantized energy model, he was able to fully describe the photoelectric effect. Let's look at a simulation. This experiment showed very, very interesting results. Results that could not be explained by the wave theory of light. Now, the wave theory of light tells us that the lamp is emitting waves, continuous waves, that are traveling across space and landing on the metal plate. If we wait long enough, then lots and lots of energy is going to be delivered to the plate. So if the electrons inside this metal are going to collect enough energy to be released from the plate, then according to the wave theory of light, all we have to do is wait. It's a little bit like connecting a phone charger and waiting for your phone to be fully charged. You just have to wait. If we increase the intensity of the light, then we should have to wait less time, in the sense that a more powerful phone charger will charge your phone faster. But it was observed that at some frequencies, some wavelengths of light, the phone never gets charged. Electrons never get released, even though we are waiting and waiting and waiting, and more energy is being delivered to those electrons. It just wasn't working. And this is one of those wavelengths. Nothing is happening. If we increase the intensity of the light, that has no effect, which is unusual. We would expect that a more powerful light, a brighter light, would deliver more energy to the electrons on the metal plate, and those electrons should eventually be charged up enough, with enough energy, to release. And we would expect them to be released from the surface and travel across the gap to the other electrode, where they make a current in the wire. It was noticed that some types of light this worked, and some types of light it did not work. This wavelength here, 690 nanometers, is a wavelength that does not work. But if we change to a different type of light, then we can get this phenomenon to occur. For example, with UV light. The UV light is delivering energy to the metal plate, and the electrons are absorbing that energy, and they have enough to be released from the surface, and they travel across the gap, hit the other electrode and create a current in the wire. We did not understand why it would work for some types of light and not others. You can see here that no electrons are being released. And it came down to our understanding of the nature of light. If we study light as being a continuous wave charging up the surface, that doesn't work. It does not explain why we do not get results with one type of light, but we do get results with another type. Instead, we needed to change our understanding about the nature of light. We needed to understand that light is composed of photons. So it is not a continuous wave of light that's arriving at the plate. It's a series of particles called photons. And irrespective of the intensity of the light, the brightness of the light, each one of these photons has the same properties as the others. So we can have a lot of those photons arriving or very few. And each one of those photons is delivering the same amount of energy to the plate. And each one of the electrons in the plate is absorbing one photon. So it now becomes important to understand the energy in each one of these photons. If the energy of one photon is enough to release the electron, then the electron will be released. If the photons are too weak, then that energy will be dissipated into the metal plate and the electron will stay where it is. So some colours of light have enough energy in their photons to release an electron, and some do not. Here is an example where these photons are not energetic enough to release an electron. But if we change to a different colour of light, then we can see that these photons do have enough energy each to release one electron. The light is emitting individual photons, and each one of these has energy. If that photon has enough energy to release an electron, the electron will absorb it and it will be released. These low energy photons arrive at the plate. They are absorbed by an electron, but that electron cannot escape with this low level of energy. The energy that is absorbed by the electron gets dissipated into the surrounding material. Some wavelengths work, some do not. If we gradually increase the energy of the photons, then we notice that there is a certain value at which suddenly we will get released electrons. These released electrons are called photoelectrons. Photo for light. There we have it. So this is approximately the threshold frequency or threshold wavelength at which zinc will release photoelectrons. The amount of energy that's needed for one electron to be released is known as the work function. And it turns out that different materials have different work functions. We are currently at the threshold wavelength or threshold frequency for zinc. If I change to a different material, for example, copper, that will have a different work function. Or platinum. Notice here that platinum, we don't have any photoelectrons being released. Presumably this wavelength is not enough. So if I increase the energy of the light, we will find the threshold at which photoelectrons will be released for platinum. Notice that these photoelectrons are being emitted with different amounts of energy. Some of them are moving very quickly and some of them are moving very slowly. This is because they're coming from different parts of the metal. The ones that are moving very quickly were at the very surface of the metal, and so they needed only a little bit of energy to escape. That is the work function. The electrons that are deeper inside the metal, they need to work their way through to the surface and then they can escape. So the work function is the minimum energy required to escape for an electron that is right on the surface, and those are the ones that you can see moving very quickly indeed. The slower electrons are the ones that have had to use the energy that they absorb to work their way through the metal and then escape from the surface. So when we are talking about the energy of the photoelectrons, it's more useful to think about the ones on the surface, because the ones on the surface only needed to absorb that minimum amount of energy, which is called the work function, and they will have the maximum energy of all the other photoelectrons. We call this the maximum kinetic energy of the photoelectrons.